Hi, Chloe. How are you?
Are you, Mom? Are you? Are you?
Wait a minute. Hold on.
Are you?
Hey,
Did you say hey to me?
I sure did. Say hey to Chloe, you guys. They don't have any clothes on right now. Sorry.
Oh. Hey, y'all.
Yes, but yes, I said hey. I think some of your classmates didn't realize that I was still having class. Because somebody sent me an email saying that we would they hadn't heard from me, and I'm going like, we're having class. So hopefully
I think a lot of people are just watching the Zooms on YouTube. I know a lot of people I've talked to, that's what they're doing.
Oh, okay. Yeah, the one from last Thursday didn't convert right, and Zoom is trying to convert it for me. So I'm waiting on them, and they got a backlog. So,
well, if anyone asks me, I'll tell them.
Yes, because I think a lot of people is like, well, you haven't been doing class, and I'm going like, yes, I have, because I know you, Allie, and quite a few people been in class. It's been about half of you guys been in class, so, and that's why I sent the email yesterday, the announcement yesterday. So, just to make sure that it was clear.
Yeah.
But I'm gonna do chapter 21. That's gonna be the last major chapter we go over. We're gonna do 18 and 24, but I have to look at my book. I don't think 18 and 24 is covered on you guys' exam. So if let me see, let me check it. I got the book right here. So that's what I gotta check. What is covered on you guys' exam? Because I'm gonna probably spend electrochemistry, lab chemistry, atomic structure, molecular structure, stoichiometry. Yeah, so this will be technically the last chapter we cover. Yeah.
No.
Yeah.
Get all of that.
Yeah.
I step on my
Yeah, this will be the last chapter we cover. And then I'm just once y'all do your test, we're gonna be reviewing for the final exam for the last couple of weeks.
Okay.
So this is full on the last chapter. We could cover stuff for organic, but I'm gonna save organic for organic.
Yeah.
That's what I'm gonna do. But we're gonna spend the last couple of weeks really reviewing for the exam, going back over equilibrium stuff that you guys need to remember for the exam. We got a lot of electrochemistry on there, periodicity, descriptive chemistry.
Are we going to get our lab midterm grades back?
Yes, I have them graded. I just haven't put them in. Part of them I had left at my desk, and I've gotten all of that stuff now. That's what ended up happening. I had left some of it at school, and I had to go and try to get it. And so I got it now. I thought I had grabbed everything, and apparently I didn't grab everything when I was there.
Okay.
So I got them now. So I had grabbed some people's stuff, and I left another part of the class stuff there. It was just on accident. It was just in a different folder. And so that's it. But other than that, everything else. So this is the last chapter we are going to cover. After we do the test, what we're gonna do. Okay. Hey, you guys, let me go answer the door real quick, and I'll be right back on. I have the screen up, and when I get the kids settled real quick, then we're gonna get started. But this is the last chapter we're covering. Once you take the test, everything else is reviewed for your final exam. Okay, give me just a second. All right, everybody. We're about to get started. Like I was saying before, this is the last chapter we are doing in the book. After that, we are doing just review. After we take this last exam, we're just gonna do review and get ready for your final exam. What I discussed yesterday was basically in the announcement was if you did not get your ACS or preparing for your ACS examination, please try to see if you can order it. I think Amazon has some. I don't know if they replenished that or whatever. But make sure that you get it, get a copy of it some kind of way. I don't know how you guys would get it. But I know there are some copies probably floating on the internet. But yes, I am making your final exam. But the final exam have to be set up as a standardized test. The exam will be in 2 parts, but it's going to be all multiple choice. That's how it's going to be set up. I think when you do the standardized exam, it is only 70 questions. Pretty much that's it. That's what you give in 70 questions. Because online we can only go to 50, I am going to do it in 2 parts. So you're going to have a 2-part final exam. And that is what I am going to do. So like I said, today we're going to finish chapter number 21. You guys, we will review on Thursday. And then on Tuesday, you will have your exam. And then for the rest of this time that we have, we're going to be just reviewing for the final. What's going to be on the final, different topics, things that you guys may not remember. That is what we're going to review. I know there are other classmates or whatever that have not been watching. Make sure you go to the YouTube channel. Zoom on the other day, it didn't convert chapter 19 for some odd reason. So they are converting. Okay, excuse me for a second. Okay, sweetheart, look. Go over there and finish. Go upstairs and watch Paw Patrol or watch Sesame Street. Okay. Okay. Thank you. So once we do that, we just gonna be reviewing and everything. That's gonna be pretty much it. Please start studying for the final exam and everything. Study like you're going to take the standardized test. Because for those of you who's going to be taking me for organic chem and biochem, you're going to be taking standardized tests if you're going to have chemistry from now on. That is just the lay of the land now. So go ahead, get your mind prepared to do that. That is the way we're going to operate when it comes to chemistry. You will be taking standardized exams. So the worksheets, go ahead and start working them. As a matter of fact, all of the worksheets that I have put up there for this semester, you need to print them out and you need to work them. You need to understand them. That will be a great review for the final. That is my suggestion to you. Make sure, print all of them out. Focus on this test right now. But after you're done, the other ones, print them out, go back over them, review. Like I said, I'm going to put some extra stuff up there. We're going to review. I'm going to make sure that you be prepared for this final exam. All right, let's get started. The last thing that we are going to go over in this chapter, in this book, is nuclear chemistry. Nuclear chemistry is very important because of a lot of things. Nuclear chemistry is used in medicine. It's used in all different types of things. So let's start out with going back a little bit, the nucleus. The nucleus is composed of two nucleons. You got protons and neutrons. The number of protons is the atomic number. The number of protons and neutrons together make up the mass number. So make sure you remember that. Now, when we get into nuclear chemistry, there's a certain way we have to write things. And you write the mass number at the top, your atomic number at the bottom, follow with your atomic symbol. I know we haven't talked about this since last semester, but this is how you write them. Now, with that, and let me put this in slide mode. Now, not all your atoms of the same element have the same mass due to different number of neutrons and neutrons in the atom. So you got what you call isotopes. Now, isotopes on the periodic table, there are a lot of them. The more common ones is like carbon. And carbon is one, they have one here of uranium. And uranium is uranium has three. Wait a minute. Why did it go back all the way? Okay, so uranium has three, and with the uranium, you have 234, 235, 238. Carbon, you have carbon 13, carbon 14, you got carbon 12. They use carbon 14 for dating. So you got different types of those isotopes. So each one of the elements that are on the periodic table, there is a possibility that it may have an isotope. Now, some of your nuclei, it changes spontaneously. And it emits radiation. Now, when something emits radiation, we call that being radioactive. That's what we call it. Now, when we refer to those as nuclides. Now, there are several different ones. How do we look at these? We look at these to pretty much tell us how do we actually look at these in a chemistry form, in a equation form. So we have nuclear equations that we look at. Now how do we, okay, sorry about that. All right, so how do we look at that? Now we look at that in chemical equations, we have to make sure that the charges and the atoms and everything has to balance. Now, in nuclear equations, what has to happen is the atomic number and the mass number has to balance. That is what has to happen. The atomic number and the mass number has to balance. This is a way of balancing the charge or the atomic number and the mass, and we have to do this on the atomic scale. Now, there are different types of radiation and that is used. Now, we got alpha radiation, beta radiation, and we got gamma radiation. Now, these are the charges on them. Alpha has +2, beta has -1. There are other ones as well that we're going to talk about. And we're going to talk about penetrating power and all of that different stuff. So we're going to talk about all of that. Now, I told you there's alpha, there's beta, and there's gamma. Now, what is the difference between those main three? And then we'll talk about the other ones, which is, it's right. Hold on just a second. You got positron emission and you got electron capture. Now, I know you guys are going like, this is really weird. Now, right there at the bottom on this table have the equations that you would use for alpha, beta, and positron and electron capture. Please study those. Make a little mark. Make sure you look at that table, table 21.3. That table is very, very important. You need to look at that so you'll know how to do that. And we'll go over a few of those. Now, let's get into it. Alpha decay is the loss of a alpha particle. Now, this alpha particle deals with helium, and you do a helium-4 nucleus, 2 protons and 2 neutrons. So let's look at uranium. Now, uranium is 238/90/92, and what it goes down to is you have 234/90 and plus the helium. Now, you guys, this math is very, very simple. Only thing you're doing is subtracting out the helium, and then you do need your periodic table. Have your periodic table by you. You need this out. Because what you do is you have to subtract out the helium first. So what you do is from the 238, you take away 4. And then from the 92, you take away 2. And then what you left with is the 234/90. And you just look on the periodic table and you find which element matches up to those numbers. That's all what they did. Now, how do the equation balance? Atomic number, 92 is equal to 90 plus 2. The mass number, 238 is equal to 234 plus 4. It's very simple math. You guys, it is nothing hard about this. This is simple math. Only thing you got to do is just subtract or add, depending on what side you adding or subtracting from with these. That is just it. This is the simplest part of this right here. That's all you have to do. So this is for alpha decay. So this is how alpha decay is set up. Beta decay is the loss of a beta particle. So it's a high-speed electron emitted by the nucleus. Now with beta, it can be written different ways. You can write it 0, -1 with the beta symbol, or you can write 0, -1 with the E. Doesn't matter. Now, what you would do is with this, you will write basically here you got iodine, which is 131/53. Now, because it's a -1, you have to add that to it to get 131, because that doesn't change, over 54. So when you balance it, it's 53 is equal to 54 plus a -1. And then your mass number is just 131, which is basically 131 plus 0. That is just it. Like I said, the math is very simple, very easy. That's all what you're doing. So that's beta. Now, gamma emission is I'm going to put it like this. Most of you guys have seen or heard of the Adventures. You have heard of the Hope. That's what they are talking about. It is the loss of a gamma ray. It is very high energy radiation, and it accomplishes a loss of this nuclear particle. It is no charge. It's 0 and 0. That's it. Only thing you do is you add it to the end, that it just comes off. That's all what you do. Now, positron emission, some nuclei decay with this, a particle that has the same mass but opposite charge of an electron. So this is where, when you get into nuclear chemistry, where you see this balance. So what you do here is 0 over 1. So in this case, where beta is negative, this one is positive. So when you see this one, let's take a look at carbon. Carbon 11. Carbon itself has about 8 isotopes. I know a lot of people like, really? You hear about carbon 14 all the time and just regular carbon, but it's a lot of isotopes of carbon. So this is carbon 11. And if you do this and you break it down, what you'll have is basically you just subtract, and you'll have 11 boron over 5 plus that 0 over plus 1 with that positron. So positron means positive, meaning that you got to have a plus sign in front of it. That's it. So down there, balancing the atomic number, 6, 5 plus 1, and the mass number is 11, 11 plus 0. That's all, you guys, with that. Is there more to it? Yes, it is. We're going to talk about electron capture. Now, sometimes, you guys, when we have electrons and when we talk about electron capture, what will happen is that the nucleus will sometimes actually capture an electron. Yes, it does happen. It will get absorbed into the nucleus. This does happen. They call it electron capture. Now, what they do here is they can do it this way, where it looks almost like beta. And what happens is 81 is just 0 over that negative 1. And then it'll be 81 over 6. And the only difference is the mass number doesn't change, the atomic number does. So that's the difference between the electron capture and beta. It's probably the same thing, but the difference is it's just that it falls from the electron clouds, it goes to the nucleus, and it actually is absorbed by the nucleus. That does happen. It really do. So that's the part of nuclear chemistry, because something is going on with the nucleus. Usually when I tell you 90 times out of 10, 90 times out of 100, 9 out of 10, the electrons drive the chemistry. That is true. You can stand on that. That is what happened. Sometimes the electrons will fall out of orbit and get absorbed into the nucleus. So sometimes that really does happen. The electrons are still controlling the chemistry. It's just that they're getting absorbed into the nucleus. And this is what that's called, electron capture. Now, where do you get some other new ones? You got your beta particles, you got your positrons. So what can happen with electron capture? You can have a proton, or they can do a positron 1 over 1 plus that, and you can get what you call the neutron, which is 1 over 0 n. So this is just some of it. Like I said, when doing this and when doing the math is just simple and easy. It's just addition and subtraction. That's all what you're doing to balance these equations. And I know somebody is saying, you should have started off with this first. And in some places, and some people, when they teach chemistry, they do start off with this, because this is easier than the regular balancing of chemical equations. But this is just another way of really balancing those equations. So it's really easy, nothing hard about this at all. So that's that. Now, there is some other calculations you will have to do in the chapter. We're going to get to that. Now, what happens? Now, anything other than hydrogen, anything bigger than hydrogen, you're going to have nuclear forces there. that you're going to have those repulsions between the protons in the nucleus. You're going to have that. Now, the nuclear force help keep the nucleus together. That's what the neutrons are there for. The neutrons play a key role in stabilizing the nucleus. So the ratio of protons to neutrons is very important. That's what helps with stability. Now, they got neutrons, proton ratios. What do you need to know about this? Neutrons to protons, you just need to know. For it to be stable, they're supposed to be 1-to-1. When you get into isotopes, they're not quite 1-to-1. When you get into the things that are radioactive on your periodic table, your lanthanide and your antinide series, most of those exhibit radioactivity. When you get into those, what will happen is you have this area of what we call the belt of stability, and it shows which nuclei are stable. But in order for them to be stable, they need to be 1-to-1. Now, if you got small nuclei, most of them are going to be 1-to-1. Pretty much anything 20 and under. So going from hydrogen up to calcium, they're pretty much stable. Most of them are going to be 1-to-1. There are a few, like I said, carbon got 8 isotopes on there. So for the most part, they are close to 1-to-1. But when you get bigger numbers, the neutrons and the protons are going to go out of sync. You're going to have more neutrons than you do protons. So that's what that is. So they call this the belt of stability, and this just shows which ones are pretty much stable. Now, you have some that are unstable. Now, nuclei with large atomic numbers that are larger than 84 tend to decay mostly by alpha emission. Now, if we pull up, and let me pull up a periodic table real quick online for you guys so that you guys can see that. Let's see, where am I? Hold on just a second. I want to pull up a periodic table. So that you guys can see that. Let's pull up the one I normally pull up in class anyway. And let me hit share, and let me hit the dynamic periodic table. All right, so they say anything greater than 84, which is right here. Now, remember I talked to you guys in class about this. This is polonium. Now, polonium is the element that was discovered by Madame Curie. Madame Curie did a lot of work in radiation. She won a Nobel Prize not only in chemistry but also in physics on this work that she did. And this is one of the things that she found out when doing radioactivity. This is one of the things they found in her notebook when she was doing her work. Like I said, the reason why I think people took pictures of her notebook is because her notebook and even her body, her bones, they are radioactive. She had to be buried in a lead box. They keep her research notebook in a lead box because of all the work. So anything above polonium, that's what they have found out, that it can be radioactive and everything. Now let me go back to periodic table. Okay, so with that, all of those decay by alpha emission. Now, a little bit later on, we're going to talk about who found all of this and did all of this stuff. But she's one of the main ones that really did a lot of work in this, her and her husband, Pierre. Now, they got a radioactive decay chain. Now, they can't, sometimes what'll happen is you got a few of them that will decay not by one nuclear transformation. Sometimes it takes a series of decays to form something stable. Now, when it does that, sometimes uranium, that's a good one. It'll go all the way down to thallium. You'll have that. Sometimes uranium will um, decay all the way down to lead, and polonium decays down to lead. And so that's one of the other things that Madame Curie found out is that some of these will literally decay until it goes down to what it is. So that's what it is. So uranium is one of them. Just a quick side note. Uranium is used to build nuclear bombs. The atomic bomb, all of that is used with uranium. We do have a site in Tennessee. We have what we call the Oak Ridge National Laboratory. They're one of the places that store our uranium. Sometimes when you have heard that, even in the news, when you talk about other countries, Iran, Iraq, and all of them, that a lot of those countries have been doing nuclear stuff, North Korea. When you hear about those countries, they can enrich their uranium to make the atomic bomb stronger that they're trying to build. So with that, you hear that, that's what they do. We have uranium here. It's stored in Tennessee. That's one of the major labs. There's some other labs that store our uranium deposits, and that's what we can do as well. We can enrich our uranium. That just basically means that it can go through these series of nuclear reactions to enrich it. That's what they're talking about. Now, there are numbers. So write these numbers down, put them on your periodic table. So 2, 8, 20, 28, 50, or 82, those numbers make sure that the neutrons have stable nuclides. Now, nuclei with an even number of protons and neutrons tend to be more stable than those with odd numbers. So just so you know, if you got something that has an odd number, sometimes they're less stable than the ones with even numbers. So keep that in mind. So over here, this is just a table that tells you that, but these are just some of the numbers: 2, 8, 20, 28, 50, and 82. Or the protons that have 2, 8, 20, 28, 50, 82, or 126. Those are the ones with the magic numbers. Those numbers are used to stabilize everything. Now, you have what we call nuclear transmutations. You can do these. They can be induced by causing particles to collide with the nucleus. That's what happened. They have these different places called particle accelerators. I have used them. I worked at Cornell. The Cornell University has a particle accelerator that the school, part of the school, is actually built on top of. And so you have to go underground to get to it. When I was working there, some of the particles that I made, just to tell you, I did a lot of work with cobalt oxide, making different shapes. And one of the things about cobalt oxide is that it is magnetic. You find cobalt in X-ray machines, and different things like that. Also, cobalt is some of the cathode material that is used in lithium ion batteries. So that's a lot of my research really dealt with that. And one of the things that we looked at is putting those particles in accelerators to see what would happen. So they have cyclotrons and they have synchrotrons. They accelerate the particles in a path which is circular. Now they have one in London, and I know y'all have heard me say, yeah, I went backpacking in London for about 2 weeks. Well, while I was over there, I wasn't over there just to backpack and have fun. I was actually over there doing research with the University of London. They have a cyclotron as well. And so what I did was took my particles over there as well and did some of that work with that. And actually, as a matter of fact, I know I know some of y'all was like, well, she hasn't been. I'm actually writing a few papers on that as we speak. So in the process of doing all this, I'm trying to get the rest of my research published on this and some of my work that I actually did over there. So along with teaching and keeping two kids at home, I'm trying to get my research published as well on that. So these are cyclotrons. We use that. I used accelerators. And so we just look at what happened because I created, it's not necessarily a new material, but a shape. And we try to see what happens with the shape. Does it make sure that if I have a certain shape, do it keep that particle stable? And how much radiation is this particle can be exposed to? Because like I said, they can use the cobalt oxide not only in batteries, which is important, but they can use it in other machines and stuff for like medical industry, for medical use and all of that stuff. So that's one of the things we've been looking at with the particles. So they have different ones. Um, the synchrotron one is at one of the national, I think it's Sandia, possibly. So we have several of these. It's one or two in California. Like I said, Cornell has one in New York. There are several of these that are around the country and around the world. So if you get to do some major research like that, you get a great way to actually travel. Now, like I said, this is how the particles accelerator look. And they are huge, you guys. They are huge. So you have the proton source, you have this vacuum pump, and I probably, if I can dig up some pictures, I will actually show you one of the rooms we were in. And so you got this alternating voltage source. And what it is they are literally miles long. They are not, no, a couple of feet. No, they are literally miles long. And then you got some of them that go in a straight line, linear. And then you got some of them that are circular that looks just like this. And so basically you got a path of the beam, you got a magnet there, and the magnet is not shown. And then you got the voltage, you got a proton source, and you got the path of the particle going to a target. And like I said, it travels for miles. So they are really big. So like these that you're looking at, this is probably, I don't know if this is the Cornell one, I can't tell, but Cornell's looks just like that. And it's really that big. So you see those. Um, you have other use of neutrons. Now, like I said, they use them in medicine. They bombard neutrons at a particle, which won't repel the neutral particle. So they use that. Most of the synthetic isotopes, you got transuranium elements after uranium. That's how they were discovered, by bombarding isotopes with neutrons. Yes, that's one of the reasons why I was doing that. Remember when I say I make a joke about trying to find a new element? I'm seriously working on that. So larger elements were made by colliding large atoms with nuclei of light elements with high energy. So that's what we were looking at. If I can bombard the cobalt, do I make a new element? Is there a new element that'll fit on there? Do I make a new material? So that's some of the questions that I'm answering as well. So how do you write these equations? Nuclear equations with transmutations can be written two different ways. You can write it out the long way that we was talking about earlier. You can write it like this, or you can put alpha in there, and you can put this plus the proton. So those are the way. And then, or you can write it like this. And this is just shorthand. It's just 14/7. It shows you that you bombarding it with an alpha particle, which is this part. And what you get out is the ejected particle, which is the proton right there. And then what you get here is the product nucleus. You got a target nucleus, and on the other side, you get the product nucleus. The best thing to do is, and my advice to you guys, write it out like you did it on number one. Then when you write it out, it's easier to write it in shorthand. So I would write it out longhand first, then do shorthand so that you'll know how this is set up. So you can see them both ways when it comes to this. Now, radioactive decay. Now, we're going all the way back. I told you guys, put something in your back pocket because you was going to see it again. And this is first order reactions. And I know y'all guys are going like, oh my gosh, she got to be serious. Yes, I am. First order kinetics. There's a reason why I told you guys to print out those sheets. Radioactive decay is a first order process. This is the kinetics of the equation, natural log of NT over N naught, give you negative KT. So this is the kinetics. And then the half-life, K is 0.693 over T to the 1/2. This is it. This is the time required for half a nucleotide sample to decay. This is very important, especially for my people, because several of you guys on here are going into medicine, whether it's medicine of animals or medicine when it comes to humans. This is very important because even little animals, they get cancer as well. And so sometimes they have to be treated because people want to extend their life just as much as human life as well. So this is half-life. This is important. Now, there are different radioisotopes and things that you see here. Now, the half-life is here, and they put it in years. A lot of the ones that you see, especially with iodine, they use that a lot in radiation and different types of chemotherapy. So you will see that. Now, first order kinetics and half-life information let us date objects called using what we call a nuclear clock. Now, this is where carbon dating come in. So the half-life of carbon-14 is about 5,700 years. It is limited to objects up to about 50,000 years old. After that, you can't really measure the radiation. And I know people go like, well, what do we use? That's where the uranium U-238 and lead-206 be used for that. So when they talk about fossils and rocks from millions upon millions and million years ago, they use the uranium-238 or the lead-206 to actually date those. So they don't use the carbon-14 dating, they use the uranium or the lead dating to do those. So that's what it is. So that is called radiometric dating. That's what they use. Now, how do we measure radioactivity? Now, when we talked about radioactivity last semester, because we did talk about this a little bit when we was talking about this in, what was it, chapter 6 and 7? Yeah, in those chapters, when we started talking about radioactivity and talking about it, there are some people that, like I said, Madame Curie, she has a unit. So activity deals with the rate at which the sample decays. Their units. Burkle was a predecessor slash contemporary of Curie. Curie used a lot of his work to do discoveries to help with her work. So he has a unit named after him, and that's one disintegration per second. And then the Curie is 3.7 times 10 to the 10 disintegrations per second, which the rate of decay, is for radium. So radium is another element that Madame Curie actually worked with. So these are some of the units. Now, where do you find some of these? You got film badges. People wear those. When I worked at Women's and Children, I had a badge because I worked, taught a lot of students that had cancer when they was up there. So even I have to have a badge when I was there. You have Geiger counters. I don't have one at the school yet. I'm gonna probably get one soon. And then you got phosphors that they use as well. And when I taught at Coastal Alabama, they have a pretty incredible rock collection that is there that we use, and we have Geiger counter there. Now the film badges. Now radioactivity was first discovered by Henry Becquerel because it fogged up a photographic plate. Now film has been used to detect radioactivity since more exposure means that there are darker spots on the developed film. Now, these badges are used by people who work with radioactivity to measure their own exposure over time. So that's why at the hospitals and stuff, that's why you see nurses and doctors that work with that. That is what they use, especially with treating people with cancer. Now, you can have a Geiger counter. It measured the amount of activity present in a radioactive sample. As I was saying, when I taught at Coastal Alabama, we had a Geiger counter because one of the professors over there that retired, um, he donated his rock collection, and he has a pretty impressive rock collection, to the school. And we had a Geiger counter there because some of the rocks that are there were radioactive. And so that's what we actually use. So we have a Geiger counter. How does it work? Um, you got a metal cylinder. It acts as the cathode. You got an anode that is there, set up very similar to almost like a battery. What happens is you have some gas in there, usually an inert gas, argon, and then what happens is the radiation gases atoms. They use either argon or helium. It creates positive charges, and it can tell you what type of radiation it is in there. And so it comes out, and you see the amplifier, and you see the counter. So we had a Geiger counter that was there that could tell you the amount of activity. So that's how that works. Now, there's some substances that emits light. They are called phosphors. Um, they have this phosphor counter. It converts light into electric response for measurement. So that is what they actually use. Now, they also have these radio tracers. Now, these are radioisotopes that are used to study a chemical reaction. Now, the element can be followed through the reaction to determine its path and the mechanism for the chemical reaction. Now, radionucleotides react chemically exactly the same as a non-radioactive nuclei of the same element. That's the only difference. They are just the same. They react the same. Um, so they have those, and so they use those radio tracers. Now they are used in medicine. So my medical people, listen up. They use those. So what do they use them for? They usually administer them to a patient. Certain elements collect more in certain tissues, so an organ or tissue type can be studied based on where the radioactive activity is collected. These are ones that are here. Iodine is used in the thyroid. Iron is for red blood cells. Of course, phosphorus 32 looks at eyes, liver, and different tumors. You have Technium 99, that's for the heart, bones, liver, and lungs. I've had that before. Thallium is heart and arteries. That takes about 73 hours. And then the sodium 24 is 14.8, and that's for the circulatory system. So I've seen some of those. I have had some of those been used before, particularly on me. to study things like my lungs and everything. So I've had those used before, and I've seen other people, and I've heard of other people using the other ones as well. Now, why do they do this? Because they have to inject you with something to do different types of scans. CAT scans, PET scans, you guys have heard of that. So you got positron emission tomography. That's a PET scan. That's what that stands for. It's injected into the patient. The blood flow, the oxygen. It look at glucose. It's studied. So labeled glucose is used to study the brain. That's one of them. And so when they put you into the machine, that's what the machine does, and it actually picks up the material that is there. So they call it sometimes, in simple terms, contrast materials. So that's what they look at. So PET scans is just one of them. Now, energy in nuclear reactions. There is tremendous amount of energy stored in the nuclei. So Einstein is the person, like I said, and I have told you guys last semester, Einstein is the one that people really didn't believe in chemistry until it was mathematically proven that it actually existed. And so Einstein is the one that really proved all of this. So his equation, E equal mc squared, relates directly to the calculation of this energy. That's where this actually came from. So Einstein actually really validated chemistry with really telling people that this is real, this is actually it. This is not just alchemy, this is just not people doing this. He really validated it. Now, to show the difference in energy, you can use the mass change associated with alpha decay of 1 mole of uranium-238 to thallium-234. And that is a negative 0.0046 grams. And so this change in energy, delta E, is basically put, delta E is equal to change in M, which is basically the mass, times c squared, which is the speed of light. That's what it is. It's very simple. So looking at that is a negative 4.6 times 10 to the negative 6 kilograms per times 3 times 10 to the 8 meters per second squared. What they got is negative 4.1 times 10 to the negative 11 joules, 410 billion kilojoules. No, make sure what that means is when you're dealing with energy, you have to put the sign to tell you whether or not energy is being released or being absorbed. And so in this case, the negative means that that energy is released. Now, where does all of this energy come from? Now, the masses of the nuclei are always less than those of the individual parts. They call this the mass defect. And then, yes, the energy needed to separate a nucleus into its nucleon. So to separate it, the nucleus, and break the nucleus down into positrons, neutrons, is called nuclear binding energy. And so this is 3 nuclei right here that they look at. So they look at helium, iron, and uranium. And so these are just 3. So mass defect. Now, so you have 2 things that can happen during this process. You can have fission and you can have fusion. Heavy nuclei gain stability and give off energy when they split into smaller nuclei. That is fission. Now, lighter nuclei emit great amount of energy by being combined. That is called fusion. So that's the difference between the 2. Now, energy, chemical versus nuclear. And I know you guys have heard in the news, there is fire burning near Chernobyl. Chernobyl was a nuclear plant back in the day that has burned. Now, nuclear energy, when we come to that, is enormous in comparison. Now, 13% of the worldwide energy comes from nuclear. So in that case, France use a lot of nuclear. Here in the United States, we use mostly gas and coal. In China, they use a little bit of nuclear, but they use more so coal. Worldwide, this is what you see. So here in the state of Alabama, we have one nuclear plant left. It used to be 3. They're down to 1, and it is up near the Alabama-Tennessee border. It is run by the Tennessee Valley Authority. So they use it up there. Like I said, it's really near or very close to our national lab. So it used to be 3. It used to be 1 that were really close down on 43, but they closed that down, I think, when I was a child, so years ago. So it used to be 3. They closed them down because people was really concerned about what happens very similar into what happened in Japan. So they don't like to use those anymore just because of safety reasons. Now, nuclear fission. Now, your nuclear power plants, this is what they use. The heavy nuclei can split in many ways, and this is what happens. This equation basically shows you that uranium-235 can split into split. So that's what they're showing here. Basically, the uranium can split with barium, krypton, and do all of that. So that's what they're showing here. Now, this is what most of your nuclear power plant use. Now, with nuclear fission, bombardment of the radioactive nuclide with the neutron, it starts the process. And once it does that, it releases transmutation. So it's releasing the transmutation strike, causing the decay and production of more neutrons. If it keeps on going, we call this a chain reaction. Now, surprisingly enough, when I was younger, there is a movie that has Keanu Reeves in it and somebody else, one of my other favorite actors in it. The movie name is Chain Reaction. It's a very old movie. Ask your parents about it. They probably know about it. It deals with just this thing, and Keanu Reeves plays one of the scientists in there, and it's another guy that plays in there that I like so well. But it is called Chain Reaction, and it talks about pretty much somebody running a nuclear power plant, and they start a chain reaction, and it blows up probably half of the country or something. So that's what happened in that movie. So with nuclear fission, what happens? You have to reach, in order for the action to just keep going, you have to reach what you call critical mass. So you have subcritical mass, where you got the rate of the neutrons lost is greater than the rate of the neutrons created by fission. Now, when you come to critical mass, that basically is in equilibrium, meaning that neutron loss and neutron creation is the same. Now, what happens is when you get to supercritical, you got an explosion coming on. That's what happens. Now, that is what happens. That's how we say weapons of mass destruction and all of that. That is how they are created. When they hit in the subcritical uranium, when they mix, they create that. So they have to reach supercritical mass in order for them to explode. So weapons that were created by causing these smaller amounts to be forced together to create this mass. So when it hits on impact, that is what happens, and it creates that supercritical mass. Now, in nuclear reactors, the heat generated by this reaction is used to produce steam, that turns the turbine connected to the generator. Otherwise, the plant is basically the same as a power plant. Now, what happened in Japan a few years ago, what you have to do every so often is take these nuclear reactors offline and you have to clean them. Like here, they have to be near river, the water going in, and so they have water that keeps it cool and everything that generates the steam. So water coming in can be 27 degrees, and then when the water comes back out, it's 38 degrees. So what happens is basically they have to keep this reactor core cool as well. And when they took it off, the reactor core over here to the left became very unstable and they failed. And when they failed, it just created some craziness. So radioactive materials, that's where all of it is in the reactor core. And what happened, that got into the water and everything. So that's what happened to the one in Japan, and that happened about 10, maybe 10, 15 years ago. So that's what it is. The reactor core consists of these fuel rods, the control rods, moderators, and the coolant. And that's what happened. The fuel element and the control rods, the control rod basically blocked the path of some neutron, keeping the system from reaching a dangerous supercritical mass. But what happened, some of these fell out of sync. That's what happened to the one there. And when it fell out the sink, even though the reactor was offline, because they were cleaning it, when they did that, when they failed, this is what created um, all of the waste and everything, and people to get sick over there. Now, the reactors have to be stopped to replace or reprocess the nuclear fuel. That's what they had to do. They are stored in pools at the reactor site. Now, the original intent was this waste would be transported to reprocessing or storage site. So a lot of times you got political opposition to storage site location and safety challenges. This has been a major social problem. That's why Alabama don't have as many nuclear plants as normal because of this problem right here, because of the waste. Now, you can also have what we call nuclear fusion. When small atoms are combined, much of the energy is released. This occurs on the sun. Those are thermonuclear reactions. If it was possible, it's easy to produce this method, it would be the preferred source of energy. But this, you got to have really high temperatures and everything. Now, how they did this, they used this in the atomic bomb to initiate fusion in a hydrogen bomb. Now, this is not the way that we're going to approach producing energy. So we're not going to do that. Radiation and the environment. So the last few things that we're going to talk about in this is we are constantly exposed to radiation. Light is electromagnetic radiation, so we're constantly exposed to it. Most living tissue is 70% water. Ionizing radiation is what causes water to ionize. This creates very unstable, highly reactive hydroxide radicals. That results in cell damage. That is what happens. And this is the equation. Water can act as an acid and a base. So that's what happens. So it becomes ionized. Now, what happens to the cells? It depends on the body itself. Now, what happens is alpha radiation just goes to the skin. Beta radiation can go to the bone. Gamma radiation can go through and through. Inside the body, alpha radiation can cause the most harm if it gets inside. Now, there are ways that you can protect yourself. What stop gamma radiation is mostly lead. So low level long-term exposure can cause health issues. Um, that's what they're talking about in 5G right now. That's the big deal. People don't understand. They don't want the 5G towers up. That's one of the things that they're talking about. The 5G towers cause a lot of radiation. It's a lot of radiation. And so that's why they don't want them up at the moment. That's why a lot of people are taking them down because of the amount of radiation that they produce. So that's what that is. That's what happens. So damage growth regulation mechanism of the cells that results in cancer. Now, there are units to measure this. One of the units is gray. GY, the absorption of 1 joule of energy per kilogram of tissue. And then the one that mostly is used is RAD, is radiation absorbed dose. The absorption of 0.01 joules of energy per kilogram of tissue. So 100 rad is basically 1 gray. Not all forms of radiation is harmful to tissue. That's why we have chemotherapies. So they look at relative biological effectiveness to show how much biological effect it is. So they call it REM. Sievert is basically the SI unit uh, for it. 1 sievert is equal to 100 rem. So number of rem is equal to number of rad times RBE. So that's what you see there. And when you talk about exposure, 600 rem is the fatal dose for most humans. 0 to 25 is not detectable. If you get 25 to 50, it's slight temporary decrease in white blood cell counts. 100 to 200 is nausea, marked by a decrease in white blood cells. And if you get up to 500, if you get exposed like that, half of the exposed population, somebody get radiation poisoning, they will die within 30 days. That's pretty much it. That's what happened. So this is all for this chapter. There's nothing else that we're going to cover pretty much in our book. There's a few things that I did wanted to touch on as far as organic chemistry and stuff, but I am not going to touch on those. I am mostly going to give you guys your final exam. I want you guys to go ahead and make sure that you got your labs done and all of that. So once you do all of that, that would be fine. The next couple of weeks, like I said, we're going to review on Thursday for the exam on next Tuesday. I'll probably open the exam on Monday because I know some people are working and everything. So I want to have review on Thursday so you can get your exam. And then after we're done with that, we're going to basically be going over what your final exam is going to consist of. So that is what we're going to look at. Now, most of the stuff on your final exam will consist of stuff that mostly going to cover this semester. So we're going to go back over some things. It may be a few things from last semester, but most of it is going to be highly concentrated on the stuff we went over this semester. So I want to reassure you of that. Make sure you get your labs and everything on in so I can get that done. Then after you finish with your exams, we're going to focus on getting ready for the finals. Like I said, the finals will be in 2 parts for that. I'm going to try to keep it between 70 questions, and because this one is not standardized, I may give you up to 100 questions. And that is just because of the fact that I'm doing it in 2 parts. The more questions you have, the more you can miss, and you can still keep a high grade for that. Study guides. Buy your study guide. I may also put a study guide out for this next test, but also what you need to concentrate on and make sure you study for your final exam. So I will definitely do that as well. If you got any questions, please make sure you send me an email and everything. I'm going to jump off here because I got to make sure your video convert before I start my next class so that I can load it up. Like I said, if you got any questions, make sure you send me an email and everything like that. I will talk to you guys on Thursday. You guys have a good one. Stay safe.